Okay, so oops. Okay, so before we continue talking about the Islamic mathematicians and algebra, I just wanted to talk a little bit about some of the Greek mathematics that we're seeing in some of the presentations. In particular, I want to talk about the concept of infinity that was used in classical Greek mathematics, which really kind of influenced how mathematicians looked at infinity till probably the 19th century. And that was a great deal of nervousness about infinity. That wasn't true all around the world. The Indian mathematicians, the ones who introduced zero, they were much more comfortable with the idea of infinity. And so this again has some kind of cultural reasons. So with the Greeks, we saw the idea of the discovery of irrationals was a little unsettling to them. So we've seen different proofs of why square root of 2 is irrational. One of them is that one where you assume that it's P over Q, and then you can see that that you can just have P and Q have as many factors of 2 as you like, which is kind of contradictory to the idea that they should have a lowest, that you can just factor out those 2's. Or we did it by doing a rectangle of sides square root of 2 by 1, and then by the process of doing a Euclidean algorithm, I think by just taking away 2 squares, you end up with a rectangle which was similar to what you started with, so therefore you could just go on forever and ever. So they didn't want to accept square root of 2 as a number, but the thing is, it's there, right? Because it's there as the diagonal of a square. So if you've got a unit square, square root of 2 lives in the diagonal of the square. So it's not there as a number, but it is there as a length. And so then they sort of so that's why they then sort of concentrated their maths in geometry, because there things like square root of 2 could exist without any problems. Okay. But this was just like in general, they didn't like infinite processes. And so to be able to do their mathematics and sort of deal with sort of infinite things, they came up with 2 types of theories. There's a theory of proportions, and there's the method of exhaustion that you would have seen both of these in the videos before. And they're both due to Eudoxus, and they both turn up, I think, in book 5 of the Elements. And so people have called this, the fear of infinity, that the Greeks had some sort of fear of infinity. And this sort of permeated sort of Western mathematics, and it wasn't really until the late 19th century that mathematicians were able to accept infinity as more than just potential. So the Greeks were okay with the idea of potential infinity. So by that I mean, consider a line. They didn't really think of a line as just really going forever and ever and ever. They think of a line just as going as far as you need. Okay, that's what I mean by potential. Or think of the numbers, 1, 2, the counting numbers, 1, 2, 3, 4, 5. They didn't really think that the numbers would actually go off and there'd be actually some sort of infinity at the end. They just meant that you can count, and you just can count as much as you need to in any sort of situation. And so the person that's credited with inciting this fear of infinity in the Greeks was the philosopher Zeno, who was around 450 BC. And so a lot of you would have heard of the paradoxes of Zeno. It's quite often brought up when we do calculus, because he was kind of like the first person maybe to consider things actually going to infinity. Now the trouble is we don't have any of the works of Zeno, so we don't really know what he said. The only reason why we know Zeno's paradoxes is because Aristotle talks about them. And Aristotle is an enemy of Zeno. He only talks about Zeno in order to discredit him and to argue against what he's saying. So we don't really know why Zeno came up with these paradoxes. And so that would be fantastic if we actually knew that. So what's a paradox of Zeno that has anyone seen? Right. So what was that one?
So you probably half the distance in time, so you take half the time and go there, and you keep doing that, but the arrow will never reach the final endpoint, even though in reality it will.
Right. So, or there's the other one, Achilles and the tortoise, where Achilles is famous because he's a really fast runner, and the tortoise is actually famous, right, because it's really slow. And you have a race between Achilles and the tortoise. And if you give the tortoise a head start, Achilles can never catch the tortoise, because by the time Achilles has reached where the turtle started, the turtle has moved a little bit. Hey, then Achilles has got a little bit more, but the turtle moved. So again, it's like there's this infinite number of steps, and how do you handle that? And so these are all things that we learn to handle in calculus when we look at the idea of a limit and the idea of a convergent series. So I've got up here the dichotomy. This is the first of his paradoxes. And so the dichotomy says there is no motion because that which must arrive at the middle before it arrives at the end, which I think is what you were talking about there. So all that's really saying is that an interval consists of an infinite number of points, and we don't find that paradoxical at all. So, anyway. So probably the earliest infinite process that the Greeks were kind of aware of was this idea of side and diagonal numbers. And so this is, you might recognize this picture as the picture that we get when we had a rectangle of square root of 2 and side 1. And so we do the Euclidean algorithm, right? We subtract 1, which is getting rid of this square here. And then, so what do we got then? So then we've got 1 and square root of 2 minus 1. Square root of 2 minus 1 is then subtracted away, so that's this square here. And then we're left with a rectangle, which is similar to this rectangle. And so what the Greeks did with that then is, well, thinking, well, let's just say this here is not exactly square root of 2 and 1, but approximates square root of 2 and 1. Then if we go out here, this rectangle will be a better approximation of the square root of 2. And so this gives a recursion relation. And the recursion relation is, well, you start off with xn and yn. So right, xn on yn is approximately square root of 2. And to get to the big one, well, xn plus 1 is equal to, it's equal to this, which is xn plus yn plus xn plus yn. Yes, yn there, so you get that. And yn plus 1 is xn plus yn. So this gives you a recursion relation. So for example, if square root of 2 is, well, it's approximately 1.4, which is what, 7 over 5. So this is my x, and this is my y. So a better approximation would then be x1 would be what, 7 plus 10 is 17, and yn be 5 plus 7 is 12. Okay, and that gives you a better approximation for the square root of 2. Okay, and so we would be quite comfortable with this, thinking that, you know, the limit, so the way that we would write it would be the limit as n approaches infinity of xn on yn is square root of 2. That we actually do some sort of infinite process, and at the end we obtain square root of 2. So the Greeks would have been very nervous about that kind of statement. They were just thinking, no, we're just approximating square root of 2. We're just getting a better approximation. They're not actually thinking that they're going to get square root of 2. Okay. So how did Greeks actually find limits? And so there's actually a problem on the homework this week where we're looking at, was it the parabola? Yeah. So they have a geometric series, and Archimedes said that the answer is 4/3. Okay. And so the way that they actually went about finding limits would be, first they would guess what the answer was, and then they would show that the answer cannot not be that. So for example, let's do a simple one. So 1 over n goes to 0. So we're all comfortable with that. So we can think of the limit of this is going to 0. So what the Greeks would argue instead, they wouldn't like this because, you know, you're doing something infinite. So what they did is they would do something finite. So for example, first thing they would say, well, maybe 1 over n goes to something positive. Okay, well, so it's going to go, so let's say it's going to some L, and well, let's assume that L is something positive. Well, the first thing to notice is that this is a monotonic sequence. They only ever dealt with things that were monotonic. And so they would say, well, if it's going to epsilon, you can never get to epsilon over 2, right? But if we let n equal 2 over epsilon, and is it this? Is that the inner? This is like, I think it, is this the ceiling function? So this is the integer smallest integer greater than 2 on epsilon. So the thing is that this sequence goes to an actual number which is smaller than epsilon. So that's a contradiction, right? So L, so we assume that L was greater than 0, we've got a contradiction. So maybe L goes something less than 0. So let's say it goes to minus epsilon, where that's less than 0. Okay, so we know that all these things are positive, but maybe at infinity it sneaks over the the minus sign somehow, becomes negative somehow. Well, again, you just say, well, if it goes to minus epsilon, at some point, it must get to minus epsilon on 2. It must go past that. So again, it's something definite. It's something finite. And it's going to do that when n is something like minus 2 on epsilon. And that's something negative, and that's a contradiction. Okay? So instead of completing it towards going to infinity, you do what's called a reductio ad absurdum, double reductio ad absurdum argument, where you assume that you want the answer to be L, so you assume the answer is less than L. I'm going to say that. You assume less than L, you get a contradiction. Then you assume greater than L, get a contradiction. And then by the law of trichotomy, i.e. numbers have to either be, if you've got two numbers A and B, either A is less than B, A equals B, or A is greater than B, you can assume that the answer is L. And that's how they got around doing infinite things. Now, of course, the big question that's asked is, well, how do you find L? To do this, you've got to know the answer before you do the problem, sort of thing. In the 17th century, which is kind of after the period that we're interested in, mathematicians took up the use of infinitesimals, which is something which is infinitely small, right? So, for example, so this is a good 17th century argument. We want to find what the slope of x squared is. So we want to find what the derivative of x squared is. So we would look at x plus epsilon squared minus x squared on epsilon, where epsilon was some infinitesimal. This would be x squared plus 2x epsilon minus x squared. Right, since epsilon is an infinitesimal, epsilon squared can be assumed to be 0 divided by epsilon. The x squareds cancel, the epsilons cancel, and you're left with 2x. So you don't take any limits at all, you just use these infinitesimals. So this was all the rage during the 17th century, the way that you did calculus-like problems. And of course, this was highly criticized. The famous figure there is Bishop Berkeley, which Berkeley in California is named after, but they changed the pronunciation. He was kind of like a 17th century Zeno, I guess you could say. And eventually in the 19th century, rigor was restored by people like Dedekind and Weierstrass, and you do all the stuff that you do in advanced calc. Remember all your epsilon delta arguments. They made everything super rigorous again by doing that. And then eventually in the 20th century, people would say, well, actually, infinitesimals are okay. You can assume that there are infinitesimals. And the reason why infinitesimals lasted so long is because you get the right answers with them. And they can be made logically rigorous. So this kind of proof can be thought to be okay. The interesting thing is, Archimedes' work, the method, is is the one who's doing the method here today? So one of the videos for that one of you guys are doing this week is on the method, which is a fantastic result from Archimedes, and it showed you how he came up with L. And so basically what he would do was he would use the law of the lever and infinitesimals. So example, to do some problem relating sort of cones to spheres, he would imagine you had some kind of balance where the cone and the sphere was balanced, and then you would take slices of the sphere and slices of the cone and show that they would balance out. And that's how he came up with his guess for how the volume of a sphere related to the volume of a cone. And he would then go and use rigorous, you know, straight edge and compass methods to prove that. But the way that he came up with, you know, the fact that what the volume of a sphere was, he knew that by using these kind of non-rigorous methods. And so this is a really fascinating work. He's probably the first mathematician to say that, you know, the way that we come up with theorems and the way we actually prove theorems are two different things. And this quote from here says, "It is of course easier to supply the proof when we have previously acquired some knowledge of the questions by the method than it is to find it without any previous method." The method was his way of using infinitesimals to do things. Interesting thing about this work was it was lost. You know, like, we know that they knew it existed because it was talked about in letters, but it wasn't actually discovered until the 1906, I think, when it was found in the Archimedes palimpsest. Does anyone know what a palimpsest is? So books used to be really rare, right? Because to make a book before paper, you had to create it with vellum, which was kind of like, I don't know, from lamb or kind of leather, and so it was really, really extremely expensive to make books. So what you would do is you would recycle books. So you'd get an old book, open it up, take the sheets and wash it and scrape it away, and then you'd sort of turn it 90 degrees and then write in the other direction. And they found this in 1906, this Danish philologist, I think it's what it's called, found this psalm book, and he realized it was a palimpsest, which is this thing of writing over something. And somehow he was able to read what was going in the opposite direction, and that was when this work was published. And then recently, I don't know, around 20 years ago, it actually turned up and went to auction. It's actually the most expensive book. It went at auction. It was the most expensive book ever found. I actually saw it in the Field Museum. It's really amazing. It's just this kind of little thing you have to look at under kind of like ultraviolet light to be able to see the works of Archimedes. That's pretty amazing. Okay, so that's how the Greeks argued. And so we've talked a little bit about the theory of proportions that came up with by Eudoxus. And so remember, it had this really sort of complicated definition that was something like, you know, A is to B is C as to D if for any integers, or positive integers, I guess you'd say. N and M. So hang on, we want to compare A, B to C, D, N, M. So if NB equals MA, then ND equals MC, or if NB is greater than MA, then ND is greater than MC, or if NB is less than MA, then ND is less than MC, which is kind of like pretty complicated way, but actually what it's saying is a length is determined by the rational lengths, right? So a length is rational if its length is a rational multiple of some fixed length. So you make some fixed length your unit, and a rational length is then all the rational multiples of that fixed length. And so what this is saying is that a length is determined by comparing it to rational lengths. Right? So two lengths are equal if and only if any rational length less than lambda 1 is also less than lambda 2, and vice versa. And lambda 1 is less than lambda 2 if there's a rational length greater than lambda 1 but less than lambda 2. So a length is determined by the rational lengths that it's greater than or it's less than. And this Euclidean solution was super successful. In fact, for 2,000 years, it was like how people define real numbers. And they liked this because it was geometric, and geometric was thought to be better than arithmetic, because if you wanted to define things arithmetically, you would have to use some sort of infinite process. Of course, what's hidden here is that there is an infinite process going over here, right? Because this is for any integers n and m. So we're really talking about an infinite number of integers, and so there's hidden in there is kind of infinity that they've just been able to sweep under the carpet. But then the trouble came that in the 19th century, people started getting scared of geometry. And for those people in college geometry, why is that? What happened in the 19th century that made geometry dodgy? So before that, there was Euclidean geometry. And so what came up in the 19th century? Is there someone doing college geometry? Sorry? Right, right. So it's that parallel postulate. Because this is not really concerned with this class, but in the next class, the sequel to this class, one of the big things was trying to make Euclid better by getting rid of the fifth postulate, which was assuming that parallel lines never meet. Because people thought, well, isn't that something we should be proving? It shouldn't be an axiom. And the trouble is, of course, that in non-Euclidean geometries, parallel lines do meet. And so in the early 19th century, along came non-Euclidean geometries. And all of a sudden, geometry was no longer the bedrock that it used to be. And so mathematicians then turned to arithmetic ways of doing things, because that was thought to be safer than geometry, because the pictures you get from geometry can mislead you. So that was kind of the birth of the idea that, you know, pictures can lead you to make false statements. And as I said before, Richard Dedekind came along and came up with Dedekind cuts, which is basically the same thing as the Eudoxian solution, but it kind of made it more rigorous, and also it was kind of more complete, because not only with Dedekind cuts can you define what a real number is, but you can define what addition and multiplication is with respect to those Dedekind cuts. So what a Dedekind cut is, you define a positive real number to be a partition of the positive rationals into sets L and U, such that any member of L is less than a member of U. So it's kind of like you take the positive rationals and you make a cut, you divide it into two, and that cut then is the real number. So it's so for example, you can define the cut for the square root of 2 to be the set of rational numbers, positive rational numbers, such that r squared is less than 2. So this gives you all the rational numbers that are less than square root of 2. And then you can, using these cuts, you can define addition, for example, to be the set of R plus Q, such that R and Q are positive rationals. R is less than X and Q is less than Y. And you can define multiplication in the same way as these. And so this makes everything kind of rigorous again. And so this is then used, you can then use this as kind of like a way to define the real numbers. Although there are other alternative ways to do that. I believe most of, if you do a class here, it's probably Bolzano-Weierstrass theorem that you're kind of using to help define the reals. And Dedekind was very proud of himself. I love this quote. The statement is so frequently made that the differential calculus deals with continuous magnitude, and yet an explanation of this continuity is nowhere given. If then it then only remained to discover its true origin in the elements of arithmetic, and thus at the same time secure a real definition of the essence of continuity. I succeeded, November 24th, 1858. Like, very Teutonic, I feel. He was a German mathematician. So yeah, so this finally sort of was able to explain what continuity is, basically. Okay. The other thing is the method of exhaustion. This is also accredited to Eudoxus. And it's like a generalization of the theory of proportions. And it goes from quantities, instead of talking about numbers, now you're talking about lengths, you're talking about regions, you're talking about areas or volumes. And so the idea there is that a region becomes known, and by known I mean we find out its area, we find out its volume, when its position among known areas or volumes is known. And of course, the known areas of volumes are things like polygons for areas and prisms for volumes. So for example, we know the area of the circle when we know the areas of the polygons that can fit inside it and the polygons that fit outside it, so inscribed or circumscribed. We know the volume of pyramid, we know the volumes of stacks of, sorry, that should be prisms, not pyramids. So here, we've got a pyramid, we're stacking it up with these prisms here. And then we could also do the same thing on the outside. But don't think of exhaustion the way that we would think of exhaustion. Okay? We would think of, so for example, the circle being the limit of the circle being the limit of like an infinitely sided polygon. Remember, they kept things finite. So they would not show some proportionality by some infinite sequence. They would show disproportionality by a finite sequence. So let me give you an example of what I mean there. So this is Euclid book 2, book 12, proposition 2, which are circles are to one another as the squares on their diameters. Okay, so what does that mean? So that's just saying that the area of a circle equals k times d squared. That there's some constant of proportionality here. Of course, we know that it's pi on 4, so he doesn't prove that, but he just proves that that it's just proportional to the diameter squared. And so the way that you do that is you take your circle and you get a sequence of inner polygons and outer polygons, right? So these are contained within the circle, and these contain the circle, and you go from one to the next one by doubling the number of sides. By, for example, going from a square here to an octagon by bisecting each side, each arc there. Okay, and it's straightforward then to show that the difference between the outer polygon and the inner polygon can be made as small as we like. And why is that? Well, if you look at, for example, between the inner square and the outer square, right? The difference is this triangle here. And when you go from the inner octagon to the outer octagon, the difference is these two little triangles here. And all you have to do is show that those two little triangles together is less than half of the big triangle there, which is straightforward to do by elementary geometry. Then at each step, you're making the difference less than half of what it was before. And so, therefore, you can make the differences as small as you like. So that kind of means that we can make an inner polygon or an outer polygon as close to the circle as we desire. Again, by elementary geometry, we can show that the area of the polygon is proportional to the square of the diameter, right? Because a polygon can be cut up into triangles, and we know that the area of the triangles is half base by height, and the base and the height are going to be proportional to the diameter. And so when we double the diameter, we double the base and we double the height of our triangle. So we quadruple the area of the triangle. So that's straightforward to show. And now we're ready for the argument with those two facts. So let that be the area of the circle with the diameter d, and assume that the ratio of the areas is less than the ratio of the diameters. Okay? So all you have to do is choose a polygon that approximates the circle sufficiently closely so that you get the ratio of the areas of the polygons is less than the ratio of the diameters squared. That's a contradiction. And by the same argument, you can do it if by greater than. And so since you've eliminated less than and greater than, the only possibility is equality. And so you get the result there. Okay, so that's kind of like a typical Greek use of finding a limit. You don't find the limit, you use finite sequences to eliminate less than or greater than, so the only thing left is you have to have that limit. Okay, that took me 40 minutes. Wow, I didn't realize that. Okay, I can save the next thing for the next class then. That's a good place to stop.